Have you ever stopped to think about how the apps on your phone or the websites you visit actually run? It's not magic, but it is this incredible story of evolution in the cloud. You know, it's kind of like a Russian doll. Each new layer of technology just wraps around the last one, hiding it away. So today, we're going to go on a journey from these big, heavy virtual machines to lightweight containers and then all the way to a future where we might not have to think about servers at all. Let's dive in.
So here's what we're going to cover. We'll start with the old way, virtual machines and the problems they created. Then we'll see how containers burst onto the scene. We'll even peek under the hood and see how they work. After that, we'll look at the next big jump to serverless, figure out what that's all about, and then at the end, we'll put it all together to help you see the big picture.
Okay, so our story starts with the original workhorse of the cloud, the virtual machine, or VM. For a long time, this was the only game in town. But as cloud applications got bigger and more demanding, well, some pretty serious cracks started to show.
And this led developers and engineers to ask a really fundamental question. For the kinds of things we're trying to do in the cloud today, are virtual machines, are they really the right tool for the job? The answer, as it turned out, was very often no.
So just look at this diagram. This shows you the whole stack for a VM. But the most important part, the real problem child here, is that box labeled OS sitting inside. Every single virtual machine needs its own, complete, dedicated operating system. It's like having to build an entire car factory just so you can use the car radio. It just creates a ton of waste and overhead.
So, all that inefficiency has some real consequences. I mean, starting a new VM can take dozens of seconds. In internet time, that's an eternity. You're allocating resources for a whole OS, not just your app. And the real kicker? If you need to scale up to handle more traffic, you have to copy that entire heavy VM. It was clear there had to be a better way. And that better way arrived, and its name was containers. This was a totally revolutionary shift in thinking. We went from virtualizing the hardware to virtualizing the operating system itself.
Honestly, the analogy is just perfect. Think about a physical shipping container. It can hold anything, right? And it can be moved by any ship, any train, any truck. A software container does the exact same thing. It packages up an application and everything it needs into one standard, portable box that can run anywhere. This side-by-side comparison, this tells the whole story right here. On the left, you've got that heavy VM with its own guest OS. But look at the right. See how the containers sit right on top of the host's operating system? They share it. And by getting rid of that duplicate OS, containers become unbelievably lightweight and fast. Now, of course, there are always trade-offs. VMs, because they virtualize the actual hardware, have this really strong security boundary it's tough to break out of. Containers share the host's OS, which, does introduce a potential security concern. But for most cloud-native apps, the massive gains in speed and efficiency were absolutely worth it.
So how does this magic actually work? I mean, how can a container feel like its own isolated little machine while sharing the operating system underneath? Well, it all comes down to some really clever technologies built right into the Linux kernel. Let's take a look. Okay, the first piece of the puzzle is something called namespaces. The best way to think about this is that it gives each container its own set of blinders. A process running inside a container can only see other processes in the same namespace. It gets its own private view of the network, the file system, and users, all of which creates this perfect illusion that it's a dedicated machine. The second key piece of tech is control groups, or C groups for short. So if namespaces provide the isolation, the walls of the room, C groups provide the limits. They're basically a resource budget, making sure that no single misbehaving container can hog all the CPU or memory, which protects the host system and all the other containers running on it. Containers also have this brilliantly efficient way of handling file systems. An image is built up in these read-only layers. You might start with a base Linux image, then you add a layer for your programming language, then another for your application code. Each layer is kind of like a commit in Git, just building on the last one. So when you go to run the container, it adds one final, writable layer right on top. And if you need to change a file that's in one of those lower layers, the system uses this clever trick called copy on write. It just copies the file up to that top layer and modifies it there, leaving all the original base layers untouched. This makes images incredibly efficient to store and share. Okay, so containers solved the big efficiency problem of VMs. Awesome. But they created a new challenge: management. all of a sudden you had hundreds or maybe even thousands of these little containers to deploy and connect and scale, and all that complexity paved the way for the next great abstraction.
And so here we are again, asking the same question, just moved one level up the stack. Do we really want to spend our time building container images, configuring all the networking, and wrestling with complex orchestrators like Kubernetes? What if we could just focus on our code?
This is the core promise of serverless computing. Now, the name's a little misleading. It's not that there are no servers. Of course there are servers somewhere. But as a developer, you no longer have to think about them. You get to abstract away the entire infrastructure and focus only on your application's logic. Serverless is really made of two parts. First, you have function as a service, or FaaS. That's where your code actually runs, in these small little functions. The second part is backend as a service, or BaaS. And that provides all the other stuff you need, like databases, storage, authentication, all as managed services you just plug into.
So how does this FaaS model actually execute your code? It's a huge shift from having servers that are always running to a model that's driven by events, where resources just spin up on demand.
Here's the difference in a nutshell. A container architecture still has these long-running services that you have to manage with an orchestrator. But a serverless architecture, it breaks the application into these tiny functions that are only triggered by events. Like an API call comes in or a new file gets uploaded. There's no server just sitting around waiting. The code just runs when it's needed.
But this whole on-demand thing introduces a really critical concept: the cold start versus the warm start. Okay, so if a request comes in and there's no idle container ready for your function, the platform has to create one, load your code into it, and then run it. That little bit of delay, that's a cold start. But if a container is already warm and waiting, it's way faster. And that's a warm start.
And get this, the difference is not trivial. A cold start can be up to 40 times slower than a warm start. This latency is a huge consideration in serverless design, and it's exactly why cloud providers work so hard to maintain these big pools of pre-warmed runtimes, all to minimize that delay for you.
All right, so we've journeyed all the way from VMs to containers to serverless. Each step we took was a higher level of abstraction, so let's bring it all together and compare the trade-offs to see what's right for different situations.
This table really sums it all up. VMs give you the absolute maximum control, but they come with high management overhead and a cost model where you pay even when they're just sitting there, idle. Containers slash that overhead and are way faster, but you're still managing the underlying infrastructure. Then serverless removes the management overhead completely, and you only pay per execution, but you give up a lot of control and you have to design around challenges like cold starts. The right choice, as always, really depends on what your application truly needs.
Which brings us to our final question. Today, serverless isn't the perfect fit for every single application out there, especially things that need to run for a long time or manage a lot of state. But this whole journey we've been on has been about abstracting away complexity. So the real question is this the final form, or is this just the next step in a continuing evolution of how we build and run software in the cloud? Something to think about.